Swayam Prabha. Digital India. Educated India.
So for this problem, HTOG will be 0.83 meters. And the next thing we would like to do is, if you go back to the question, we wanted to find the height of the packing. So H can be written as HTOG times NTOG. Okay, so now the next task is to find NTOG. So NTOG we will do it. We will calculate by analytically. Okay, first we will try to do analytically, then we will do graphically also. Okay, so NTOG analytical. So I'm going to use this expression that we derived for NTOG. Can you please check if I have calculated the absorption factor A before? A we obtained, right, because we used it for calculating HTOG. So A value is 1.306. Sorry, this should be also mx2. Y1 minus mx2 by y2 minus mx2. In this problem, x2 is 0. So y1 is this is mole fractions, 0.0658, y2 is 0.005, and if you calculate, you will see NTOG is about 5.75. If you have a calculator, please calculate this and make sure this is a right answer. So now you can calculate the height of the packing, NTOG times HTOG. So that is 5.75 times 0.83 comes out to be something like 4.77 meters. Is something close to 5.75? 5.78. 5.7. Okay, so up to first decimal is correct. So that means we have answered the problem question that height of the column is 5.77 meters. The second approach is I already discussed about calculating NTOG using a graphical construct. Okay, so let us also do that and compare that with analytical result. So what you see here is the a plot of the equilibrium line and the operating line. Okay, so let me show you how I calculate that, how I plot those two functions. So first what I will do, I choose a range of x and y values, mole fraction values. So this x and y are the mole fraction of liquid and mole fraction in the liquid and the gas. So you can see that I have chosen a range of x and y values. Okay, and this range you decide based on the y1, y2, x1, x2. Okay, for our case, the maximum y is at y1, which is 0.0652. Okay, and y2 was 0.005, but I have taken 0. Okay, and Correspondingly, you can calculate the equilibrium x values. So x and y here are basically the equilibrium mole fractions. Okay, this we know that y is equal to 0.455x. We know the equilibrium line because we know this follows Raoult's law. And only thing we have to know is what range of x and y value we should be interested, and that is based on the operating line. What is the inlet composition, outlet composition? Based on that, you choose a range of y and range of x values. Then you convert them into mole ratio units. This is capital X and capital Y. Okay, and if you plot these two, capital X and capital Y, you can generate this blue line. Okay, so this is the equilibrium line. The next thing is to calculate the operating line. That is a red line, and the way you do that is again we already have derived the operating line equation based on the L by G ratio, and then you choose a range of xy values, and that would be the red line here. Okay, based on the material balance, we have already solved the liquid to gas flow rates, inlet outlet compositions are known. So pretty much we know about the equilibrium line on operating line. All we are doing it here is we are choosing a range of xy value and plotting these two lines. Okay, so now I go and I import this figure in here. Okay, so now what we need to do is, if you recollect, the way we calculate NTOG is by looking at a midpoint between the operating line and the equilibrium line. Okay, so for example here, so this is your y1, this is the corresponding y star. Okay, y1 is in the operating line and the corresponding y star is in the equilibrium line. So this is the total driving force, and I take the midpoint somewhere here. Okay, and similarly I take another point somewhere here, and then I find the midpoint here. So like that, at a different values of y values, you can get the midpoints and you can connect them. Okay, so I'm going to draw this midpoint line. Note that this need not be always a straight line. This can be also curved depending upon the curvature of the operating line and equilibrium line, but here it happened to be almost linear. Okay, so what I'm doing, I have the equilibrium line, I have the operating line, I go to different y values along the operating line, and I find the corresponding y star from the equilibrium line, and I find the midpoint between these two, and I mark those points. Okay, and then I connect these points. That is the line shown here in light blue. Okay, so this is the midpoint line. Then what we do, I start from the x2 y2 composition, and I go horizontally and then hit the midpoint line, and I measure this length, and I go further, I continue further for the equal length. So I may go somewhere here, I may even go beyond the equilibrium line, that's fine. Okay, the only thing to be noted here is this length and this length are actually equal, and then from here I go vertically and touch the operating line. So from here I go horizontally and then touch the midpoint, measure this length, and then continue for equal length further, and then from here I go up vertically and continue this process. Something like this. And then you can count the number of NTOGs, 1, 2, 3, 4, 4 point something. Okay, so this is something done ad hoc without a scale or ruler. If you do it in your graph paper, you will get exact number. Okay, so I have done it in my iPad here. I've got something close to I I got about 5.5. So here this is just an illustrative purpose, this is not exact, okay, because I have not measured the distances equally, I have just shown qualitatively. But if you do it properly with measuring the length of each segment and do it, you should be getting a value of NTOG about 5.5. So from here you can calculate the height. And this comes out to be something like 4.6 meters. So we have looked at two methods of finding out NTOG. One is using the analytical expression, assuming straight line, equilibrium line, straight line, operating line, etc. Dilute mixtures, that's an assumption. Or you could find the number of NTOG by this graphical construct. This is option 2. Option 3 is to do this by numerically. So for this, I have given a set of equations for getting NTOG, but I am going to use this particular form for this calculation. So here the NTOG is given in terms of mole fractions, small y. So you can look at your notes, you can see that there is a range of NTOG expression given, sometimes in logarithmic scale, sometimes in linear scale, sometimes in mole fraction units, mole ratio units, so on. So for this problem, I have taken this particular form. So in this expression, since we know y1, y2, we can directly calculate the second term. Only the first term we have to calculate numerically. Okay. So for this, let me show you the Excel sheet. So I go to this operating line x and y, and then I convert back into small x and y, which is a mole fraction, and then I find the corresponding y star. For each y, okay, there is a y star below based on the equilibrium line. So you find the y star, then you calculate 1 over y minus y star. Okay, that's the value that you want to integrate out. Okay, and you take that and then you plot it. Okay, then you will have this kind of a plot. The y axis is 1 by y minus y star, x axis is just y. Okay, so this plot I will import here. So this is on the y axis, you have 1 by y minus y star, and here we have y. Okay. So the way we have constructed this diagram is to look at this, go to this operating line, choose a range of y values, correspondingly y star values, you find y minus y star, and then you take the inverse of that, you plot that as y axis and the corresponding y here. Okay. So now as per this expression for NTOG, all we need to do is we have to just get the area under this curve. Okay. Going from y2 to y1. So y2 is 0.005 and y1 is 0.0658 or something. Okay, so now we need to find the area under this curve. So to find the area under the curve, you can use any numerical method, but the way I have done this is a very simple approach. So I find the average y value between two consecutive values, and that is this h, and then I find the consecutive x values, and then I just multiply delta x delta y. Okay, and that would be my area, and I can sum this area. Okay, or you can use a trapezoidal rule, Simpson rule, whatever you know. Okay, that's the other way. Or here I have just, since I know the discrete point here, I am taking the height of these 2 points. Okay, and then I find the midpoint here, midpoint here, midpoint here, and I basically draw curves like this. Okay, and I know the delta y here, and I know this height. I can get the area of each of this rectangles, and I can just add up. Okay, So, or any other numerical algorithm you can use, the total area you can get something like 5.87. So, here 5.87 plus 0.5 times ln of, this will be 0.995, this will be 0.9342, and then if you solve this, you will get something like 5.91. This is NTOG. So, based on this NTOG, you can calculate H. Which is 5.91 times 0.83, and you get something like 4.9 meters. So, to summarize, so if I calculate H values, this is let us say analytical, graphical and numerical. Okay, so there are 3 ways to do this. In the analytical case, we got 4.77 meters, graphical is 4.6 meters, and this is 4.9 meters. Okay, so you can see they are all almost same ballpark. So, so in this problem, this determination of tower diameter is something is left to you to find out. We have calculated the FL, FG, and then HTG, HTL, HTOG, and then the fourth part is computing NTOG and the corresponding packing height using analytical, graphical as well as numerical method we have found. Okay. Finally, this part is something I have not discussed, so I will discuss this also, computing NTG and HTG and then packing height. Okay, so this is also something we will discuss how to do this. So far, any questions, any confusions? Clear? You know how to do numerically, analytically and graphically, all 3 methods. Okay, so so now let's look at this. HTG is already calculated, so now we need to know how to calculate NTG. The difference between NTG and NTOG is that in NTOG the driving force is Y minus Y star. Okay, the concentration difference between the operating line and the equilibrium line, that's the overall driving force for the gas phase. Whereas when you do NTG, you will see that the driving force is Y minus Yi, the interfacial concentration, not the corresponding equilibrium concentration. So that's the difference between NTG and NTOG. So let's go back here and then do this NTG calculation. So for the NTG calculation, I am using the expression for NTG based on this logarithmic expression. This was also discussed in one of the class. So as you can see here, this part is easy to calculate because we know y1, y2, and the difficult part is this integral. So now again, what we need to do, we have to do in the logarithmic y, and then we have to find this expression y divided by y minus yi. Okay. So let me again tell you. So here, this is y and x. Let's say this is your equilibrium line, and let's say this is your operating line. Okay. At any point y, there is a corresponding y star you can see, and this is the driving force y minus y star, which is used in the calculation of NTOG. Okay. But when you calculate NTG, what I want is I want the interfacial concentration, not the equilibrium concentration here. Okay. And having y here, there will be corresponding yi somewhere here on the equilibrium line. So the question is, how am I going to calculate this yi? Any ideas? how do I find the interfacial concentration yi for any y on the operating line? Driving force line. So it depends on the ratios of the mass transfer coefficient kx, ky. That is only for dilute limit, but here we are using for concentrated limit. So we need to find an equation for the driving force lines. Okay, there will be several such lines. This need not be a straight line, by the way. Okay, for every y on the operating line, there will be a corresponding driving force line that will reach the equilibrium line, and from there you are going to read the interfacial concentration yi. Okay. So in order to find this driving force line, we are going to use this mass transfer of a concentrated mixture, where we wrote Na is Fg times ln of 1 minus yi by 1 minus y, and that must be equal to Fl ln of 1 minus xi by 1 minus x. So here this x and y are the pair of compositions along the operating line. This xi and yi are the pair of concentrations on the equilibrium line, and the connection between those two are made by these parameters Fg and Fl. Okay, so now I can solve for yi from here. So 1 minus yi by 1 minus y is going to be 1 minus I think this should be x and this should be xi. Yeah. So if you look at this expression, this tells me that what is the interfacial concentration yi when I start with the sum x and y on the operating line, and I know the slope or the ratios of the mass transfer coefficient Fl and Fg. Fl and Fg we already calculated, okay, based on the correlations. We know that value. What I am going to do is I am going to choose different xy combinations along the operating line, okay, and I substitute that for x and y here, and that is going to give me a relationship between yi and xi. Okay, so that is the equation of this driving force line, and I am going to calculate those lines for many such xy values along the operating line. Okay, do you follow? So what I am trying to do, I am writing a expression for mass transfer on the gas phase and the liquid phase in terms of the interfacial concentrations. Then I get an expression which relates that for any combination of xy value on the operating line, there is a corresponding interfacial concentration related by this equation. Okay. So going back to this Excel sheet, what I am going to do is I am going to choose a range of xy values here, right. These are the xy values on the operating line, okay, and I am going to substitute those xy values in this expression for x and y, and I will get a relationship between yi as a function of xi, okay. So then I generate this xi and y value from those lines, okay. I am going to choose a range of xi values and then calculate the yi values from the driving force line, and you get a set of values, and I plot that line, and that would be one of these lines here, okay. So you can see this line starts from a xy on the operating line to the terminal point. Then if you look at this line, this is based on another point on the operating line starting from here, since I know the slope of Fl Fg, and this orange line is obtained. And if you look at this line, this is based on the xy combinations on the operating line here, and then the corresponding driving force line. So and you can continue to this. So here I have shown some 7 lines, but you can actually make infinite number of lines, right. I just did 7 because I need only 7 or 8 points, but you can do as many as you want. You can take any point somewhere here, you can use any xy value in between, substitute that in the driving force line, and you'll get an equation relating xi and y, xi and yi, and you can draw a corresponding line. The point I am trying to make here is that for any point along the operating line, you can always draw a corresponding driving force line, and the driving force line will cut the equilibrium line, and that is the value of yi. For this y, this is the yi. For this y, this would be the corresponding yi. So I can get a series of y values and yi values. This has to be differentiated from the y star. For this y, I could have taken y star as somewhere here, but I am not doing NTOG, I am calculating NTG, where the driving force is y minus yi. Okay. In the previous example, we looked at y minus y star, which is easy to get because you can correspondingly get the y star from here. But here I am interested in the interfacial concentration, so I have to read from here. For the same y, this is yi, this particular point is yi, whereas this is y star. Okay. So then you can see after that what I do is, for those y values, I correspondingly get the yi values from this plot, and I find y minus yi, that is this value. Okay. And I am basically plotting that as a function of log of y. Okay. And I will get this particular curve. So I am just importing this in the presentation here. By the way, I will share this Excel sheet for you, so you can also check this later. So here, yeah, so we have y by y minus yi plotted as log of y. Okay. So now by our definition of NTG, which is here, all I need to do is I have to find the area under this curve going from log of y2 to log of y1. Okay, so that is the area under this curve. Fortunately, in this case, since I am using in the logarithmic scale, I get a pretty much a linear line for this. Okay, so I fit this linear line into a linear equation and I just integrate this out. Okay, and if you do that, you will get NTG as something close to 8. And then we have already found that HTG is 0.59 meters. And if I calculate H using HTG and NTG, I get something like 4.72 meters. So whether you calculate the packing height based on the NTOG or NTG, the height is pretty much the same. Okay, but which is easier method? NTG or NTOG, which is easier to do? NTOG is easier to do because you can see how much work we have to do for getting the interfacial concentration, and you have to get a lot of this interfacial concentration by drawing the driving force lines. Doable, but it's quite cumbersome. On the other hand, if you use overall NTOG using the interfacial using the equilibrium concentration instead of the interfacial concentration, it's far more easier. You can do graphically, you can do numerically also, fairly easy. Okay, but still I wanted to highlight this point because you should probably know how to get even the NTG itself also. So this is based on numerical NTG HTG. You get about 4.72. So you can see that these values are not very different. In this case, the analytical result also very close to the numerical and graphical because these equations are equilibrium line and operating line are almost a straight line. But the other problem I have given as an exercise problem, you will see the equilibrium line is quite curved. Okay, so there you will see a lot of difference between the analytical result and the graphical or numerical result. Okay, so this is specifically designed such a way that all these results will be almost the same. Okay, so my suggestion is to kind of, you should be familiar with calculating packing height for dilute mixture as well as the concentrated mixture. When it comes to concentrated mixture, you should know how to do it through graphically and numerically also. Okay, using both overall driving force as well as the local driving force. So that's the context of this. So if you look at this problem sheet, there is another problem. Problem number 4 is given, which you have to do pretty much the same way that we did the previous problem. Okay, the only difference is I have changed the packing material, and the problem equilibrium values are given based on problem number 1 here, and this is quite concentrated mixture. Okay, so I kind of suggest that you try to solve this problem on your own using the methodology. So you can see that we are going to exactly do the same thing. Calculate the tower diameter based on the pressure drop, calculate all the mass transfer coefficients and HTG using the same correlations that we used in problem number 3, and then computing NTOG and the corresponding packing height analytically, numerically, as graphically. At the same way, do the same thing for NTG and HTG also. Okay, so try to make sure you do this by yourself, and if you have any questions, you can always reach out to me. Yeah. All the necessary values are given like the previous problem. Okay, so for example, you can see this porosity is given, liquid hold up is also given. So all the things that you need are given. Okay, so you just have to practice how to do this problem. Yeah. Okay, so that's it for today. So we are done with absorption. All kinds of absorption we are done. So next class onwards, I will be talking about distillation. Okay, that's it.